Thank you, Konstantinos, for the introduction, and thank you very much to the organizers who put up this very nice workshop and gave me the opportunity to present my work. So I will mostly talk about numerical methods, and I decided to put a lot of things in this talk. Maybe it was not a good idea, but it's based on a series of works and works in progress. Started in 2022 with this paper with De Angelis and Germain, and then with the Chaparro and Parcheschi, we continued this work with 2 more papers, and so the first 2 are actually works. You can find them on arXiv, and then the last 2, the ones with Matisse, was here, I think. I don't see him. Yes, he's there. And Menozzi, who's unfortunately not here, is still work in progress, soon to be on arXiv. I don't specify what soon means. And another one with Matteo Cagnotti, who's also here, who's my PhD student. This is not going to be soon on arXiv. This is his PhD work. Okay, so what I will do, I will start with introducing what kind of SDEs we're interested in. And in particular, they have distributional drifts. And before going to the numerics, I want to make an overview of how you solve these SDEs from a theoretical point of view, because this distributional drift poses problems in already defining what a solution is. And so I will explain you what has been done in the literature, what are the methods, and some of them are better suited for numerical methods, which is what I will then do in the second part of the talk. I will review some literature. I want to focus on SDEs with distributional drifts. Of course, there's a lot of literature on numerics for SDEs, also for numerics for SDEs with irregular coefficients, but I really want to focus on the one with the distributional coefficients. And then I will present the main results that we have. And one is about strong error. This is in one-dimensional setting only, and we have additive Brownian noise. And the second main result is about weak error. This can be done in d dimensions, and the noise is an alpha-stable additive noise. If you have questions or you want me to repeat something, please interrupt me. Okay, so the SDE, many of you know it actually, but I'm assuming not all of you are familiar, so I'm going again through the basics. So the SDE is, like I said, additive noise, and the drift, and we want to, so the main aim is to set up a numerical scheme for this. But the point is that the drift B is a distribution in the second variable. So in time it's a function, actually it has to be even C1/2 or C alpha. So anyway, it's a at least continuous function in time, but in space it's a distribution. And the noise is additive. This is very important because when the noise is multiplicative, things get a lot more complicated. So additive noise really helps. And mostly in the talk, it will be Brownian motion. And the numerics will be mostly in dimension 1 because in dimension 1, we have strong solutions of these equations, and we do strong error. In dimension D, solutions exist, but are weak solutions. And then at some point at the end, this noise here will be an alpha-stable noise. And that will be in dimension D, and we will look at the weak rate in that setting. Again, the solution of star is weak. Okay, so it is interesting, this is from, well, probably many of you know this, but there is this interesting effect which is now been named, well known by regularization by noise, where if you have an equation which is this one here, this is deterministic, which describes some phenomenon, for example, where this B is, for example, the quenched realization of some not necessarily Gaussian random field. What do I mean by this? I mean This is the realization of a random field, or the derivative of the realization of a random field. Quenched, namely, you fix the omega. So it's really a very rough object. Then you cannot define this equation. I mean, even if it's not that rough, this equation is not well posed. Even if this is a function, but is not Lipschitz, this equation does not have a unique solution. So it's not well posed. And you can, however, if you add the noise, additive noise, then this perturbation regularizes. So the noise really helps and allows you to give a meaning to this equation, even if B is a distribution. Okay, and the first works in this direction, where B is not a function, where T dot is not a function, the second variable, are in the early 2000s, 2003, 2004, by Flandoli, Russo and Wolf, and Bass and Chen. And they were looking at time homogeneous, in fact, distributions, but of specific form. In this case, they were the derivative of continuous functions or measures of Kato class. And then, a few years later, these two works appeared on arXiv very close together. And since then, a lot of works, I think this field started really to bloom. But in both these works, the B is time dependent. And it's a distribution in this case in a Besov space of negative order minus beta. And here in this other work with Flandoli and Russo, we were looking at fractional Sobolev spaces, again of negative order. The threshold, so you can go below 0, but not too much below 0. And if you make use of rough paths or regularity structures or paracontrolled calculus, you can go beyond 1/2. Otherwise, if you stick with the so-called Young regime, you're stuck to 1/2. So minus 1/2 is the lowest threshold that you can achieve. Okay, and like I said, after that, many other people started working on this. They generalized to various, to dimension D. The work by Delarue and Dir was only in dimension 1. People started looking at other noises like alpha stable noise or fractional Brownian motion by Atreya, Budkowski, Mitnick. They did alpha stable, and Ancelotti, Richard, and Tarret, fractional Brownian motion. Paul-Éric, Chadur-de-Raynal, and Stéphane, they were doing alpha stable noise and time-dependent drift. And then also literature started appearing on looking at the estimates for the density of the solution. And these, I think Zhang and Zhao did the Brownian case, Perkowski and Van Julen, I forgot, also Brownian, and Fitoussi, the alpha stable case. Okay, and then, I mean, numerical schemes are quite natural, I think. At this point, we know quite well the theory. We know a lot about how the solutions look like, and numerical scheme are a natural thing to do. But like I said, before actually going to numerical schemes, I want to just briefly tell you how you solve these problems in theory. So there are, I would say, two main ways, plus one, which is the third one, which is very useful in numerics, so that's why there are three, in fact, but conceptually there are two, I think. So the first one is what we named the Raff-Martingale problem, because essentially it's you phrase your SDE as a Martingale problem. So you try and find a class of functions for which are called test functions, for which when you take a function in this domain of test functions, the some quantity is a Martingale. I'll show you later. And this is the classical Martingale problem. And this way, you can avoid defining B of t x t dt, because of course, when B is a distribution, you cannot evaluate it in a process, because distributions must be evaluated in test functions. and x is definitely not smooth as a test function. So with the martingale problem, you get rid of defining this b of txt. This has been used by the work in the Delarieux deal in 2016, extended to dimension d, and then used by other authors in different settings. The second type of solution is what I like to call local time type solution, but also, which is very close to limiting argument. Limiting argument solution, and this is the main idea is to say, okay, I don't know what b is. I approximate b with a sequence bn, and then try and see what happens at the limit. If I get something which makes sense, that is the meaning I give to my equation as a limit of something. Okay, and the third one, which is actually useful in the numerics, is what we introduced in 2017. We called it virtual solutions. Is a bit on the side. It doesn't really fit in either of these two, and it's based on a Zwonkhin transformation. You essentially try and remove the drift b, which you don't like, with a Zwonkhin transformation, get another equation which you can solve. But it's called virtual because you really just don't solve this equation, you solve another one, which, if b is smooth, coincide with the original one, but if b is not smooth, you didn't really give a meaning to the original equation. Okay, so one slide for the details of these three notions. So, rough martingale problem, you have to identify a domain of test function, which is this dl, such that whenever you have an f in this domain, the quantity f of xt minus f of x0 minus the integral of lf ds, it's a martingale. So if you think of the classical martingale problem, this f is C2, or C2 with the compact support, and L is the generator of the process. So if b is a function, L is this. Okay, the time derivative, the Laplacian, which corresponds to the Brownian motion, and then gradient f times b, which corresponds to the drift. Right. Now, the thing that happens is that if now this b is a distribution, first of all, gradient f times b is not, I mean, you have to define it, but this is possible with pointwise products or paraproducts, if f is regular enough. And it's still a distribution, however, so you can define it, but you end up with the regularity of b. So it's a distribution. But what happens is that you can solve the PDE LF equals g where you choose g. So you choose g to be a function, and then you solve the PDE, and you take all the f's which solve the PDE LF equals g, and this is your domain. So now what you've done is that when you take the f's in this domain, if you're able to solve the PDE, then LF is g. So here you don't have LF, but you have g, which you chose. G is a function. And so this writing here is well defined. Okay, and that's the main idea, and of course you have to work and solve the PDE. So the notion of solution, the notion of martingale problem is the one that comes from Etienne-Courts. It's linked to weak solutions. That's why we talk about weak solutions, because martingale problem is linked to weak solutions in the classical setting. We don't have we don't have a notion of weak solution for the SDE with distributional drift. We have the notion of martingale solution, which we call weak solution essentially. It heavily relies on the well-posedness of this singular PDE, the LF equals G. You have to be able to solve it and to show some properties, like stability. So if Bn converges to B, or if Gn converges to G, Fn converges to F, and so on. And essentially, this singular PDE is very linked to the Zwonkhin transformation. So the operator L is the same one that appears in the Zwonkhin transformation. Okay, and with this notion, you can look at different kind of noises, but still noises that have a PDE underlying. So you can do Brownian motion, alpha stable. You cannot do fractional Brownian motion. In dimension 1, you recover strong solutions. So you can show that if you set your Martingale problem in dimension 1, then the solution you find is actually a strong solution. And however, there is no dynamics. So I defined my solution as, in fact, sorry, I go back. My solution is a couple, where is it? XP, such that whenever I take f in the L, this quantity is a martingale under P. So I don't have a dynamics, and this for numerics is not very good because you don't know what to simulate. So if you want, you can reconstruct the dynamics. For example, Chaudhry-Renal and Menozzi did it in their paper where they have, here they have alpha stable noise using nonlinear Young integrals. Okay. Second type of solution, this is a local time type solution. So here you have to introduce this operator, which is, well, plays the role of the local time in a sense, which is the extension. This operator ax applied to B is essentially the integral of B Sx SDEs, right? This is what you would like to have. However, this integral is ill-defined, so you define it for the L's for which this makes sense. So in this case, we did it in CT C0 plus, so continuous functions in time with values in C epsilon Hölder functions in space. And if you can extend this map AX, which is well defined on CT C0, to some set B, B typically will be a space of distribution. So think of C minus beta, where this beta is between 0 and 1/2. A set B which contains the little b you're interested in, then the solution is just xt equals x0 plus this, which plays the role of the integral of b, plus w. And that is more or less the same as the limiting argument I was describing below, where instead of, you don't know what b of where is it? Of txt is, so you mollify the b with bn's that are smooth enough so that you can define bnt of xt. And then you say a solution is a couple xw such that whenever I have a sequence bn that converges to b, the limit of bnt must converge to some process k such that this equation holds. So it's very similar, not the same, however, because here in the second one you define the notion of solution specifically for one fixed b. It's like you're defining the integral for one function. Instead, in the top one, you're defining an operator which works for every b in a class. But essentially, they are the same object. The good thing about this is that it allows, it doesn't rely on PDEs, and so you can work with fractional, you can use this for fractional Brownian motion. And this was, well, we used it with Francesco in the case of Brownian motion, and described the process as a weak-Dirichlet process. Atreya, Budkowski, Mitnick used it with together with a Zwoncki-like transformation, and also compared it to virtual solutions, which is the third type that I will describe later. And instead, Anzelletti, Richard, and Tarret used nonlinear Young integrals to define this K operator. Okay. And again, in dimension 1, you recover strong solutions, also in this setting. This I already said. Very importantly, you can use fractional Brownian motion, which you couldn't in the first with the Raff-Martinger problem. And to do that, you make use of the stochastic sewing lemma, basically to define K. Oops, sorry, I keep doing that. The good thing about this is that, well, at the limit, it provides the dynamics of the process. So this looks like it's better suited to define the scheme. However, then to prove that the scheme converges, you still don't have the limiting object. I mean, the limiting object is K, and you don't know what it is. It's a limit. So it looks a bit better, but I don't, yeah. Okay, and the third one, it's the virtual solution, which is the one we actually use to do the computations in the numerics. So this is the idea of the virtual solution, like I said, is that you want to get rid of the drift by applying, by doing what Swankin did. You apply a transformation, which is given by, where is it here? Given by the solution to this PDE, where L is the operator of the, so it's the generator of the SDE, formal generator. Again, this product needs to be well defined, but I already told you we know how to deal with the PDEs of this form. So if you apply this, if you take a solution U to this PDE and you apply Ito's formula to U of txt, suppose that U is C2, which is not, and xt exists, which you don't know, but formally, what you get is this equation. And now here, the good thing is that B is gone. There is no distributional drift. And U is actually C1, so the gradient of U exists, and there's a bit more. So the gradient is alpha Hölder continuous for some alpha. So this looks like something we can treat, but is still not written as an SDE because this term here, it's neither a drift nor a diffusion. And so then what you do is you kind of take this and move it on the other side and call x plus u of tx y, this phi here. And then you write an equation for y. And this equation for y is standard. I mean, u is well defined, gradient of u is well defined, there is a drift, a diffusion, everything works. Okay, so the virtual solution is a solution to double star, where we removed b and we, instead of b, place this colored term. So it's not the solution of the original equation, it's a solution to another equation. However, when b is smooth, they coincide. And it was proved by various authors that actually all these notions of solution are the same when they're all defined. Okay, so then what you do is you solve the y, and once you solved it, you transform back to go to the x. And here also you do weak solutions because it turns out that the regularity of u is not enough to guarantee strong solution. And so y can be solved, but it only has a weak solution, and therefore x is weak. Okay, and this writing double star or the equation for y is actually very useful when you do numerics, when you try and show the convergence of the scheme, because here you really have a dynamics, you really have objects you can write down and compare the norms. Okay, and so this is, like I said, it's based on this Swankin transformation, the removal of the drift, this what Swankin did. You need to be able to solve the PDE and have some properties. In particular, you need to be able to invert this Swankin transformation, which you can do. Again, in dimension 1, you recover strong solutions. The drawback is that you solve another PDE, SDE, but it has been shown that this is equivalent, to Raff-Martinger problem, and it's good because you have an explicit dynamics that you can use to do computations. Okay, so questions on this first part? Okay, so let's move on to the numerics. So let me start with a brief overview of some works with low regularity coefficients. And So here the coefficients are still functions, but with low regularity. There is a series of work by Michela Sorgeni and co-authors, Leobach and Neuenkirch and Pribilovic, where they essentially have drifts, but also, okay, first of all, they have multiplicative noise, and then they allow for irregularity like discontinuities. So here the drift is discontinuous, or some part of the drift is in a Sobolev space, and they also look at jump diffusion SDEs, again with discontinuous drift. So the drifts have jumps, they allow drifts to have jumps. And they get strong rates of, well, order, depending on the setting, 1/2, or something of this form. And most of these works are based on a transformation of the SDE. They apply a transformation where they remove these discontinuity points and get to another SDE which doesn't have the discontinuity points, for which they can apply standard methods and then go back. This transformation is not like Zwonkhin, it's really very different than that. Okay. Then there are these two works by well, Oleg, Konstantinos, and Mate, and Konstantinos, Mate, and Koa, where they looked essentially at well, alpha Hölder continuous drifts, both in the case of additive noise and multiplicative noise. And they, so here with alpha Hölder continuous drift here, and also, well, it's not alpha Hölder continuous, but W dot alpha, so it's the regularity is alpha, is measured with the same alpha, but here they are not continuous in this second paper. They are in a W space, and what comes out is a rate of the form 1/2 plus alpha half. Also here, okay, this is fractional Brownian motion, so plus alpha times h, minimum 1. And with the multiplicative noise instead, the rate is a bit less. Well, this is expected, so it's 1/2. The alpha doesn't appear here, and same with same in this other paper. Okay, so this one. Oh, sorry, I keep doing that. This 1/2 plus alpha half. It will appear later on again. So if the regularity of the drift, which is a function, is measured by alpha, so it's alpha Hölder continuous or in a fractional or in a Sobolev space, fractional Sobolev space of order alpha, then you get a rate which is 1/2 plus alpha half. Which also means that if alpha is 0, at the limit when alpha is 0, so say basically you have bounded measurable, then the rate is 1/2. Now we go in the realm of distributional drifts. And the paper, I only know of my own works and a paper by Goudenège, Harès, and Richard. Two of them are here in the audience. So Ludovic, Harès, and Richard, they dealt with fractional Brownian motion. And they work in d dimensions because with fractional Brownian motion, you have strong solutions in d dimensions, depending on the Hurst index. If you want to go higher with the dimension, you go lower with the Hurst index. The rougher the noise, the more regularizing effect it has. And so you can go to any dimension as long as h goes down and still have strong solutions. Their drift is in a Besov space of order gamma, with gamma that must satisfy these regularity conditions. So think of B infinity, so this doesn't appear. Gamma is bigger than 1 minus 1 over 2h. This already appeared yesterday a couple of times. And so if you want to tackle distributional drifts, namely if you want gamma to be negative, h must be smaller than 1/2. So they do not cover the Brownian case, or they cover the Brownian case, but the drift is not a distribution when h is 1/2. So if they want to have a distributional drift, they must have h smaller than 1/2. However, they work in dimension D, and they find a strong rate of convergence with this order, 1 over 2 times 1 minus gamma. They do LP, so LM in omega, and also C1/2 in time error rate. And the way they do it is by essentially, they use because they work with fractional Brownian motion, they have to use the limiting argument solution, and they deal with the stochastic sewing. They use stochastic sewing to deal with the estimates. Okay, and then we did, well, with the Andres German and the Chaparro and the Parchesky, we did the case of Brownian motion. We had to stick to dimension 1. We wanted to work with strong rates, so dimension 1 is where we have strong solutions. And okay, in the first work, we were working with fractional Sobolev spaces, and in the second work, we were working with the Holder spaces, Besov spaces, sorry. But more or less, the ideas are the same, and however, the regularity here is restricted to 0, 1/4. This because there is this Q which is bigger than 4, so it restricts that. Instead, in the Sobolev space, in the Besov space, we go all the way to 1/2. We get a rate in L1. However, this rate is not optimal because when beta is 0, so beta is the irregularity parameter. So when beta is 0, this C0 is more or less bounded measurable. And so we would like to recover what was obtained coming from the positive side, which was 1/2. The rate was 1/2 in bounded measurable. And instead, we are at 1/6, so well below the optimal. So what? Okay, this is the result, and how do you set up a numerical scheme for a distributional drift? And in fact, this I call it blueprint, is more or less the same way that Goudenège and co-authors did. So what you have to do, because B is a distribution, first of all, you remove B and replace it with Bn, where Bn is a function. Otherwise, on the machine, you cannot do anything. And then once you have Bn, and let's say Xn is the solution of that, you then apply an Euler scheme, because then with Bn, this is suddenly all is well posed, all is smooth, you can just apply Euler scheme. So you have the parameter n, which is the smoothing parameter, and the parameter m, which is the Euler scheme parameter. So m is the number of steps in the time 0t. And then, you call ks the running time, t ks the running time. The Euler scheme is really just the standard Euler scheme. But there are these two parameters, and we don't like to have two-step schemes. We want to have one parameter. So we have to combine, basically we have to choose one as a function of the other and come up with a one-step scheme, one parameter scheme. Okay, this will be done at the end. How do we estimate the error? Well, you split the error into two terms. One part, I don't know why I start with B, this xn minus x is stability, so you want some estimates that say if Bn converges to B, then Xn converges to X. Okay, so this is stability estimate. It doesn't have to do with numerics, and it's quite standard, but B is a distribution. So it's a bit tricky to find these estimates. At least we found it tricky. In fact, that's why there is this F here, because we didn't find a standard stability estimate where F is the identity. But we have a power. We have Bn minus B to some power, which is smaller than 1. So we don't like it. And then you control the other term, which is the Euler scheme. So in principle, this is classical. It's an Euler scheme. You can use just classical methods. What is the catch? The catch is that classical Euler scheme uses Gersonov theorem. And Gersonov theorem will have an exponential dependency on the norm of the coefficients of the drift. But the norm of the drift will explode. because the Bn is smooth, but it converges to B, which is a distribution. And so if you just apply classical Euler, your estimates will blow up. Okay, but if you do these two estimates, you combine them, and after that, you choose one in terms of the other, and then you get a scheme with one step. And so the main result of the first paper now I stated a bit more precisely. So, like I said, dimension 1, B depends on time. Some numerical papers have B time dependent, but most they just get rid of T and do time homogeneous. Here we still had time dependence. We have to increase the regularity in time compared to well-posedness. For well-posedness, you don't need 1/2 regular. But for the numerics, we need 1/2 regularity in time to carry out the procedure. And then in space, it lives in a fractional Sobolev space of negative index minus beta, which goes all the way to -1/4. This is due to this Q, which is between 4 and 1 minus beta. And we find an L1 rate. So we cannot do LP, in fact. We only have L1, and the supremo is outside. The rate is explicit in one parameter. Like I said, we chose M, which is the discretization of the Euler scheme. It's explicit, but it's really ugly. I will show you. This is the rate. The rate is 1/2 minus beta times gamma minus 1/2 times theta star, which is this. So explicit, but for sure this is not optimal. I will show you a plot later. And this, maybe, yes, here. And like I said, at 0, so when beta is 0, namely when I'm in the realm of more or less bounded measurable functions, I get 1/6, but coming from above, it was 1/2 plus alpha half. So when alpha was 0, the rate was 1/2. Okay, so certainly not optimal. And the way this rate is constructed, and I will highlight here where I think we lose the optimality, is like this. The Euler scheme estimates are quite standard in the sense that you get two terms that depend on the Euler parameter. M is the parameter of the Euler scheme. So there is m to the -1 and n to the -1/2 with two coefficients in front which depend on capital N. And this is important because then I will have to choose capital N as a function of m. And these C1 and C2 explode as n go to infinity, because they look at the norm of Bn in L infinity, at the derivative of Bn in L infinity, and also at his Hölder semi-norm in 1/2. And the worst of these terms is the one in blue. So I have m to the, because m to the -1 and -1/2 help, they converge. And they explode, the C ends. And this is the fastest exploding, this is the slowest converging. And here is where we lose optimality, I think. In the second part, the estimate is the stability. And we use virtual solutions to do all these computations. So we do essentially the stability for the process Y that I described before, and then go back to X. But this transformation, there are some bits which are alpha Hölder continuous, and in doing this back and forth, you get this power 2 alpha minus 1, which is tiny because alpha is is tiny. It's big. Alpha is bigger than 1/2, so at least it's positive, but it's nowhere near 1. And so here is again where we lose optimality. So then we combine these, we choose n optimally with respect to m. That is what gives us this very rough, very bad rate, very complicated rate. And we should be able to do better if we get rid of these blue terms, which is work in progress. So how, I already said a little bit, how do we do that? We use the definition of virtual solution, so we transform into this y process, and then we use the Ito-Tanaka formula for the absolute value of y minus yn to compute the error. And so, because we're doing that, we end up with local times, which is another reason why with this method we cannot go higher dimension, because we're using local times. So we got inspired by this paper by Jan, where we're using another local time. And then, of course, we use heavily the properties of the solution U and of the stability of the solution U, which is the solution to the singular PDE. So we really know a lot. The singular PDE, which is the one used to transform from X to Y, we know a lot. We have all convergence results that we need. Okay, and one last thing. This is in this setting, for this paper, we were using fractional Sobolev spaces, and we also used Haar and Faber bases to express Bn as a series that then we cut. And Haar and Faber bases are nice for numerics. They may be nice for numerics because they are piecewise constant or piecewise linear. I mean, Haar is Faber is the integral of Haar. So Haar is piecewise constant. And this means that when you write an element as a Faber series and then you cut, then you can write this function without error in the machine, because it's a piecewise linear, piecewise constant function. So it's enough to know the value on a number of points, big enough, and then you know the function exactly. Okay. And then the other paper, which deals with the Besov drift, it's very, very similar. So similar technique. All the spaces were different, but the techniques were the same, and the rate also is the same. This R is, in fact, exactly. Sorry, where is it? Here. No, sorry. The rate is not the same, but because there is no Q. But also is not nice. It's there is this power 2 and well, not optimal. Again, when beta is 0, we get 1/6, and we get vanishing rate when beta is 1/2, which is actually to be expected, because when beta goes below 1/2, the whole theory cannot be applied. The solution does not exist in this setting. You can make sense of a solution using rough paths or regularity structures, but in our setting, when you go beyond 1/2, solution doesn't exist. And so the vanishing rate at 1/2 makes sense. Okay, so in this second paper, we also did the numerics, and this was nice because, well, how do you plot a distribution? So I had quite some fun. So the idea is to take a function which is very rough, well, which is not differentiable. And the example we got was fractional Brownian motion. And then you differentiate it. So in the plot here, the green line that you see in the middle is a path of fractional Brownian motion with Hurst index 3/4 here, and with Hurst index 1 here. And then we took the derivative. Of course, the derivative doesn't exist. You cannot plot it. So this is a smoothed derivative, smoothed with the heat kernel. And the smoothing parameter is called n, capital N. And when you see two, I think you see them, two lines, one is green and one is red and one is green. The green one oscillates more than the red one because the smoothing parameter is higher. So as n goes to infinity, this thing will oscillate to infinity because it becomes a distribution. So this this green oscillating line is what we plug in the drift Bn. And then the rate we get in practice is much better than the rate the theoretical rate. This is the theoretical rate. This is 1/6 here. This is 1/2. The green line here, sorry, the green line on top is 1/2 minus beta half, which is the equivalent of 1/2 plus alpha half that was obtained for alpha Holder continuous function. So if the regime would continue from positive to negative regularity, it would be the green one. And what we get is this line here. This is the numerics is this red one. And this is just to show what the density of the solution looks like at time 1. So you start with the standard Gaussian x0. You run the numerics for time 1. The drift on the left picture is the drift from the left picture before. So this drift here was in the space c minus 1/4. Instead, the drift on the right-hand side is in the space C0, more or less. So it's much smoother. And the other thing I want to point out is that, I don't know if you see, there is a green line which covers the red line. And because we computed the density in 2 different ways. The green line is, we solved the Fokker-Planck equation and plotted the corresponding Fokker-Planck equation. And the red line is the Monte Carlo histogram at time 1. And they fit really quite well, so this was, comforting to see. Right, so we are improving the rate. There's one first improvement, which is, which you can see in Matteo's poster on Thursday, and the pitch today, I think. Where he worked with LP rates instead of L1. So this is the rate, this ugly rate that we have in L1, but we are not able to work in LP, and he worked out how to do it in LP. And for P, obviously, it's also this is not optimal, but at least is in LP. And these are 3 values for 3 different P's. And also he's working on trying to remove the this bad term that came out from the numerics, and he managed. This is still nowhere to be seen on the archive, but he should write a paper soon. So with being able to remove this term and replace it with this, the rate, which was this one so far, became this one. So now we are at 1/2. Which is much better. However, you see, it's still not linear. I mean, we would expect something linear with the rate. And so we're still working, and the reason this is not working is because the stability estimate still has this power. Okay. Yes. We also did the case of McKean-Vlasov SDEs. So we treated the case where the drift B is depends on the density of the solution, and has this form in particular. So f of r is the third variable, f depends on rho, and then it's multiplied by a distribution. We did the similar things, and we get the same rate, because we use the same techniques. However, here what we have to do is, because we don't know rho, so we did 2 things. Either we assumed that rho n is given to us, and it's known analytically. And if this is the case, more or less things go on like in the previous case. And then say, okay, instead, suppose you have a solver for rho n, a PDE solver, that preserves certain norms. So that basically it preserves the norm that appear in the rate, the infinity norm and the derivative of the infinity and the infinity norm of the derivative, then the rate is the same. So if your PDE solver is good enough, then you can carry out the numerical scheme, plugging in, instead of rho, which is unknown, your solution to the Fokker-Planck equation, and then solve as a standard SDE. And these are the results. So the top one is used with the nonlinearity sin x, which I call the linear nonlinearity, because x is small actually, so sin x is really just linear in the regime where x lives. And you see it's really quite, they start again from standard Gaussian. It's really quite smooth. It's really quite stable as standard Gaussian, more or less. I mean, it has a different shape, but instead, the bottom one has a nonlinearity because it's sine of 10x. And then you can see the effect of the distributional drift, especially here on the left side, the beta is 1/4, while on the right side, beta is 0. So this side is a bounded measurable function. Here we are in the realms of distribution. And again, it fits that also in this picture, there is the green line, which is the one that we get from the Fokker-Planck solver, and the red lines, which are the histograms from the numerical scheme, and they fit quite well. Okay, so that was, I still have a couple of minutes. That was for the strong error. And the other work that I wanted to present is the joint work with Mathis and Stéphane. Well, this is the one that is soon to be on archive. So here we have additive noise, but it's alpha stable process. And we work in dimension D. And the drift is time dependent, is LR in time, and it takes values in Besov space of order minus beta PQ. So there are lots of parameters, sorry, but under certain conditions for alpha and beta, which are the standard one for alpha stable processes, the well-posedness has been proved by Schadruder and Allen Menozzi, and Matisse proved the density estimates for the solution. And then, I will skip this. And then, with knowing that there is a weak solution, we went on to try and set up an Euler scheme and study weak error. The Euler scheme is, so I cannot skip that bit. Yeah, the Euler scheme is defined with this matfrac B, which, so let me go back, sorry, which is coming from the way they were able to reconstruct the dynamics. So half an hour ago, at some point, I said, if you define the problem using the rough martingale problem, you can still define the dynamics via nonlinear Young integrals. And that's what they did in the paper. They defined the dynamics. So they defined this object here, which is essentially a semigroup applied to B. And then what we did was just say, okay, this B then is our numerical approximation of our drift. So we plug this B here, and this is the Euler scheme. And the computations we do, however, are not of a strong error, because we don't have strong solutions, but are of weak error. In fact, we work on the densities. So we compare the density of the original equation, which is called gamma. Gamma starting from x, going to ty. That's the process starting at time s in x, going at time t in y. This is the density which has been found by, the bounds have been found by Matisse in this paper. And the same can be done for the density of the Euler scheme. So you have Duhamel representation for gamma. So gamma appears on the left, but appears on the right too, because it's this expectation of x, which is computed with gamma. And same here, gamma h appears here and appears here. And then you can, what we did was to compare gamma h and gamma using the Duhamel representation. And so you compare the terms in the Duhamel representation, and you find a rate which is essentially gamma over alpha. Alpha is the alpha stable, the process is alpha stable, so alpha is that parameter. And gamma is the gap to singularity, so it's the space you have left for well-posedness, essentially. Well-posedness asks that beta is bigger than a fraction, whatever. And the gap to well-posedness, the gap to singularity, is what gives you the rate. And this was, by the way, the same rate that was found by Matisse, Jordan, and Menozzi in the LPLQ case. They found gamma over alpha with alpha gap to singularity. So same. Okay, and I will stop here. I think I will stop here. Thank you.
Thank you, Elena. Any questions?
Well, thank you very much for your excellent talk. Yeah, could you go back to? I was curious about what's your rate depending on the n, on the modifier n. You didn't show the.
On the previous one, on the modifier.
Yeah, because there's only beta. Yeah, how about the n?
Yes, n, capital N, you mean?
Yes, a capital N.
So that's where is it? Let me see. Yeah, okay. When do you, let me go to, yeah, here. So we write xnm minus x, split it in these two, then we have these terms plus these terms, okay? Now, what happens is as n goes to infinity, bn minus b goes fast to 0, so we would like n to go fast to infinity, but when n goes fast to infinity, these explode. And this, but Bn, B capital N, is really defined, maybe I skipped that, is defined as the semigroup at time 1 over n, B. So we know exactly how fast all these things explode in terms of n, and then we choose n as a function of m. We postulate n is m to the power theta, minus theta, well, and we just optimize. We see which one is this. One wants to blow up, the other wants to go down, and the optimal theta is chosen. That's why we get this weird rate.
And could you give some, or if any optimal or some suitable choices of this theta?
Of the?
Of the theta, of this, the relation between capital N and little m.
Well, with this estimate, the optimal choice is the one we found, but it's really not. This is theta star.
Oh, sorry, I'm sorry. I mean that if your capital N,
yes,
maybe some power of the little m.
Yes, exactly.
And what, yeah, this is
so this is m to the power theta. That's exactly the computation we did, and that was the theta, which is clearly not, but because the estimate is not optimal. We don't have optimal estimate in the,
Thank you, thank you.
Hi. Thank you very much. I probably just missed this. It's a very silly question. On the plots, when you say you compare to the PDE, is this only in the Brownian case you mean?
Yes.
Or, okay.
Yeah,
okay.
We did Brownian case both with the standard SDE and with the McKean SDE, but both were Brownian.
But their beta goes down to -1/4 or something?
Yes. Well,
as a -1/2 is the
this is only, actually
Brownian.
The plots are -1/2 actually. So
okay.
The -1/4 was our very first paper where we worked in fractional Sobolev spaces with the Q, and the Q was bigger than 4 and it's restricted to, Okay. So the plots were all the way to -1/2. Sorry, because I only plotted beta equals 1/4.
Yeah.
Yeah, we have the plots with beta equals 1/2. They just didn't fit, and I thought, okay, I'll just stick to this one.
Sure.
Yeah. We did it.
Thank you.
Maybe I quickly ask, what would be your rate if in your the stability you got power 1?
1/2 minus beta. Which is, for a long time I was saying I have to get 1/2 minus beta half because this is what you get with the positive, right? But then 1/2 minus beta half would not vanish when beta is 1/2.
But why would it have to vanish?
Well, because we don't have well-posedness of the...
Yeah, but also in higher dimensions you don't have, let's say with Brownian motion, you don't have well-posedness for negative regularity, but the rate at 0 regularity is still 1/2, it doesn't vanish.
Okay, yeah, I don't know, I don't know. So the numerics actually shows 1/2 minus beta half. If you see what we get, it really looks like that. But if the stability is linear, we get 1/2 minus beta, and it vanishes at 0.
Then let's say
Okay.